All right, so in this video, we're going to take a look at some examples of derivatives, limits, and integrals that we discussed in the previous one. So we closed out the last video talking about how when we find the limit of a vector-valued function, the result is itself a vector. And to do so, we're just going to take the limit of each component separately. So I'll need to do a limit as t approaches 1 of 3 over t squared, a limit as t approaches 1 of the natural log t over t squared minus 1, and the limit as t approaches 1 of sine of 2t. So this first one here is pretty easy. We can just plug in the 1 and we get a 3 that comes out of it. The last one is also pretty easy, where we plug in the 1 and we get a sine of 2 that comes out of it. However, this middle one here, if we plug in the 1, you'll notice we get a 0 over 0, which is an indeterminate form. Now it's an appropriate indeterminate form to use L'Hopital's rule, so that's what I'll do. So LH for L'Hopital, I'll have limit as t approaches 1. The derivative of the numerator would be a 1 over t. The derivative of the denominator would be a 2t. And you could simplify this as you need, or you can reevaluate as you are now, and you'll see you get a 1/2 out of that. So this limit up here is going to be the vector 3, 1/2, and sine of 2. And that would be a pretty straightforward process there in evaluating that limit. All right, so in this example, we're going to be taking this vector-valued function here, and we're going to find the parametric equations of the tangent line to this vector-valued function at t naught equals 2. So if you'll remember from the last video, whenever we take a look at some curve, this guy right here we'll say is our r of t. Then when we go ahead and take the derivative r prime of t, that's going to give us the vector tangent to that curve at that point. Do keep in mind, I mentioned it and I pointed you to a specific page in the text to explain it even more. These two are not necessarily perpendicular. Okay, so not that that's really going to come into play here, but I don't want you to be misled by my picture. Okay, so if we think about this now, we're coming up with the parametric equations of a tangent line. And that means we need two things. We need a point and we need a direction vector. Well, the point is going to be pretty straightforward. I'm just going to go ahead and take 2 and plug it in here, and that's going to give me the point. Once again, watch my notation here. It's going to be written as a point, not as a vector. So natural log 2, e to the negative 2, and then it looks like we have an 8 that comes out of that. So I took the 2, plugged it in there, and there to get this point right here. Now for the direction vector, as you can probably guess, we're going to take that derivative, which is going to be a vector, and it's going to be pointing in the same direction as, of course, what we want. So the r prime of t is going to be a vector, and we're going to go component by component. This guy, then this guy. So that'll give us a 1 over t, negative e to the negative t, and then 3t squared would be our derivative. I'll take this now and evaluate it at 2, which is going to give us now the vector 1/2, negative e to the negative 2, and then a 12. So this guy right here is going to be our point, and this right here would be our direction vector. So now we'll put together our parametric equations of the tangent line. That's going to be an x equals natural log 2 plus 1/2 t. If you remember, this is going to be the x coordinate of our point, and then we have the component that's going to be out in front of the parameter, the component of the direction vector. And so now our y will be done similarly, where we have e to the negative second minus e to the negative second t, and then z would be the 8 plus 12t. So that would be the parametric, or those would be the parametric equations of the tangent line to this curve at this point. And again, you can see that these are the coordinates of my point, followed by the components of my direction vector. All right, now before clearing the screen and moving on to something else, I do want to point out a certain couple formulas This is page 754 of your text. These are the differentiation rules for vector valued functions, and none of it will be a surprise to you at all, but I do think it's important to point out that you have, since you have essentially two different products, you have a dot product and a cross product with vectors, you're going to have a dot product and cross product rule when it comes to their derivatives. And the dot product rule won't surprise you. The cross product rule, in fact, might not surprise you. But it's important to remember that the cross products are not commutative. Dot products are, cross products are not commutative. So the order in which you perform that differentiation is very important. The book does a good job. They actually have a proof of both of those underneath the box. And it's just something I really wanted to point out to you more than anything. It's unlikely you'll use it a lot, but it is something to be very aware of as we move forward. All right, so the next thing I want to talk about is again an extension of something we've already talked about many times with the calc sequence. If we let vector valued function r be a position vector, then when I take the derivative of it, I get a vector, and it's our velocity vector. The magnitude of that velocity vector is speed. That's going to take off the direction that this would have. This will have direction associated with it. When I quantify it, that takes away that component. So that's going to be our speed. Then if I take the second derivative of our position, which is the first derivative of our velocity, that's going to give us acceleration, and it's going to be an acceleration vector. Okay, so really no surprise there. Additionally, that also means that if I integrate my acceleration vector, that's going to give me velocity, and if I integrate velocity, that's going to give me position. And so again, works the same way as it would have earlier in the course, earlier in the sequence. So I'll go ahead and clear this now, and we'll take a look at an example. All right, so in this problem, we're given the acceleration vector, we're given some initial conditions, and we're going to work this all the way back to come up with our position vector, of course, given these conditions. Okay, so just like we would have in earlier coursework, I will go ahead and integrate to get this thing started. So when I integrate acceleration, I get velocity, and I'm going to integrate term by term here. So this would be a -3 cosine 3t. This would be a 3 sine 3t, and this would be a 4t. Now, it's technically plus c there at the end, but that c is a c vector. And so if we're going to add or be able to add two vectors, they have to be the same size. So this is going to have to be a vector with three components. And so let me go ahead and change that not to the c vector notation, but instead I'm going to say c1, c2, c3. Okay? Which if we go ahead now and we need to evaluate at v0, so 0, that's going to be a -3 cosine 0 plus c1. Then I'll have a 3 sine 0 plus c2. And then I'll have a 4 times 0 plus c3. So I went ahead and evaluated at zeros there. And then knowing that I'm adding c1, c2, c3 to the correct components, that's going to now be set equal to 2, 0, -7. So 2, 0, -7. And then we can just solve. We have -3 times cosine of 0, which is 1. So -3 plus c equals 2. So -3 plus c1 equals 2, which implies that c1 would equal 5. Then similar for this one. Sine of 0 is 0, so that's going to very directly say that c2 is equal to 0. So c2 equals 0. And then, much like the last one, 0 plus c3 would be c3 equaling -7. So I'll come back here and revisit my v of t as -3 cosine 3t plus 5. Then I'll have my 3 sine of 3t and my 4t minus 7. So all I did is I went back up here and I plugged in the c1, c2, c3 back to the original v function. All right, So we've got our v. Now we need to go one more step. So I'll integrate. If I integrate v, I'll come up with r, which is our position. So as I integrate this now, I get negative sine 3t plus 5t. I'll get a negative cosine 3t. And then I'll get a 2t squared minus 7t plus our c. Much like the last one now, I'll need a c vector having 3 components. So how about c4, c5, and c6? Now I'm ready to use this initial condition. So r of 0 would be a 0 from this guy right here, plus a 0 from this guy here, and then plus c4. And so again, this plus this right here for our first component. Then I'll have my comma. And now I'm ready to evaluate this at 0. So that's going to give me a negative 1 plus c5. So negative 1 plus c5. And then finally, I'd have a 0, 0, and then a c6. So 0 plus 0 plus c sub 6. Close that up. And we know that that's got to be equal to the 3, 4, 0. And so now, much like we did up here, I can see that C4 is going to be equal to 3. So C4 is going to be equal to 3. Negative 1 plus C5 is going to be equal to 4, which means that C5 equals 5. And then finally, C sub 6 would equal 0. So C sub 6 would equal 0. I'll go ahead and put all this back together, and I think we're going to have it. So final answer here, negative sine of 3t plus 5t plus 3, negative cosine 3t plus 5, and then finally 2t squared minus 7t. So that would be our final answer. That would be our final position vector given these initial conditions. And so to come up with this again, all I did was I went back into here, I plugged in the 3 for C4, and we went back into here, plugged in the 5 for C5, and the 0 for C6, giving us, again, our final answer without any constants.